Recording to the cloud. I think hopefully my screen is big for anyone online while this is recording and I'm not sharing screen. If it just shows Mars's name in big letters, then this is not ideal. Today, we're going to be starting by talking about tolerance stackups and tolerance analysis. We'll look at that in just kind of a handwritten notation. We'll look at it in terms of Excel, MATLAB, and then we're going to transition into SOLIDWORKS. But these things are reasonably straightforward in terms of understanding how they're going to operate. So if you think about the most basic stack up that we can really write out is if I have a set of parts that align with each other kind of on their faces. So these can be cubes or blocks or whatever it is, right? And each of those parts has some known variance or a tolerance. So it is 1 inch plus or minus 0.1 inches. And I can say this is a 1/2 inch plus or minus 0.1. Maybe this one here is 1.2 plus or minus 0.05 inches. And then this last one, well, maybe 0.75 plus or minus, let's say 0.03 inches, right? And I could have just made those all plus or minus 0.01, but you get the idea. I can look at the variance, right? I'm just gonna use sigma for variance of each part. So if I have part 1, part 2, part 3, part 4, then I can write out the variance of each of those parts. And so I have 0.01, 0.01, 0.05, and 0.03. And all these are in inches. Kind of important that they all have the same unit values, right? Then the total, we got this going to be 0.1, 0.2, 2.5, or 0.25, 0.28, to be plus or minus 0.28 inches. So that would be the variance on this stack up here. And I'm going to add up the total lengths too, although I don't necessarily care about the lengths in terms of this analysis. I do for the purpose of the assembly. But whatever this length here is going to be plus or minus 0.28 inches. And the question from a design standpoint is that plus or minus 2.28 inches appropriate for whatever I want this stack up to be? Some angle, so this is theta, this is some length L1, and then so there's some other angle here, some say theta 2, and this is L2, and I have a parameter of interest, say it's the position along the x-axis, this is x and y, of the endpoint of this linkage, so I'm going to call this just x. I can figure out how each of the parameters inside this linkage affects this distance x. Again, if I only care about the variance here, in this case, I have 2 parts, but each of the parts has 2 parameters that are going to impact that length x, right? So in this case, I'm going to have a L1, L2, a theta 1 and a theta 2. Oh, sure, this is L1, theta 1. Let's not in terms of part first. So theta 1, L2, theta 2. And a lot of times in an analysis like this, you might list the variance associated with each part and then a weighting factor. Basically, how does that change of that parameter change the ultimate thing that I'm looking at? And most of the time when I look at this, I'm going to say, okay, I'm going to treat each of these as being independent. And so I'm only going to vary one of them at a time. So if L1 is, say this is both 0.1 plus or minus 0.1 inches for the lengths, I'm gonna say plus or minus 1 inches for the lengths. And if this is, say it's some angle in degrees, I can say that my theta 1, theta 2, they've got some plus or minus, let's say 2 degrees. Sometimes holding angular tolerances in long inches is difficult because of the compliance of the mechanism. So maybe that's not terrible, right? Maybe there are gears and there's 2 degrees of play between the gears that control them. So there's a lot of variance there. So again, I can say that my theta 1, my L1, they have a variance of 0.1 inches. These ones have a variance of plus or minus 2 degrees. And then what I'll figure out is what do I need to multiply these things by to figure out how that's going to change my parameters. So if I want to look at the distance here, changing the length L1 by 0.1 inches, making it longer or shorter, is only going to change my X by whatever that L1 times my theta 1 is, right? So I can say the weighting factor here, since this is cosine, if I get the length along the x-axis is cosine of theta, I can say that this is cosine theta 1. Again, I would just use whatever the standard value of theta 1 would. I wouldn't use the change in theta 1. Right? It is 1 millimeter. Does that make sense? And then for my theta variance here, I think about what is the difference between cosine of this angle and cosine of that angle. A little harder to figure out because now the length and my value are going to change. So if I look at the maximum condition of this total distance, let's look at this right here, right? This is really L1 cosine theta 1, right? So the change in L changes that pretty easily. But if I wanted to look at what the change in theta 1 is going to be, how would I do that? Right? If this is theta 1 is constant, the derivative of this is just cosine theta 1, right? If L1 is constant and theta 1 changes, then the change of that is going to be sine of theta, right? The derivative of cosine is sine, derivative of sine is cosine. So in this case, I would actually say that the weighting factor here is going to be L1 sine theta. Make sense? And if you think about that a little bit more, it should make more sense. When this is flat, when theta is 0, right? Then changing theta does not change the x value very much. That makes sense? If this was straight up, then changing theta would have a big impact on x. At 90 degrees, a small change is going to change this. Again, 90 degrees just becomes sine. Sine theta becomes 1, right? So it's going to impact that. So I can figure out whatever the equation is I have for these parameters, I can derive that equation relative to each of the terms and then use that to figure out what's going to happen. Again, same thing here, L2, since I have this theta relative to the x-axis, is going to be cosine of theta 2. And since this parameter is pretty much the same thing as the previous parameter, we can just write this as L2 sine theta 2. Because the change in length along this axis is really just going to be this portion of that add together. And you don't have values here, but you can plug all those in, you can get the total value from that. Does that make sense? Really what you would do is you want to do this in something like Excel. So I can open up Microsoft Excel. Go blank workbook. I'm going to share a screen. Share screen. And we just list out my parameters. Sometimes it's just the name, something's out, the variance, and then whatever my factor is. I'm gonna do it for the blocks here. It's a little easier. So say B1, B2, B3, B4. Again, you might have 0.1, 0.1, 0.05, 0.03. And then in this case, they're all 1, 1, 1, 1, 1. In this example here, because they're all valued 1, right? And then I can multiply those together. So total equals to this guy times this guy. Drag that down. And then just do the sum of those values. If I want to do the second one there, I could have my parameters be, let's just copy these over. L1, theta 1, L2, theta 2. And we could say 1, what should we say? We said 0.1, 2 degrees. Probably I should convert to radians. I'm saying equal to radians. Oh, not rand. Of 2. So that's actually the conversion from degrees into radians. Equal radians 2. That's because if we ever do any multiplication of terms, and a lot of computer programming languages, they're going to use an angle in terms of radians as the default. So if I say equal to sine of an angle, the number input to that needs to be in radians. I don't know if there's a sine D. There's not a sine D in Excel. But here we can see the factor is equal to cosine of my theta 1, which actually didn't specify what theta 1 is. I need to specify the actual value of theta 1. Let's say it's, I don't know, 30 degrees. Why not? I need to actually convert that into radians as well. So radians, 30 degrees. Probably I should add an extra column here to leave this out. Let's just do this. We'll do the actual value. So L1 we'll say is equal to 5 inches long, 30 degrees, 4 inches long, 25 degrees. And we can refer to those. So we can actually use that value there. This one's going to be equal to L1, so equal to our length 1 times sine of our theta in radians. So I can do radians. Sorry, we wanted to do of our, yeah, so that's right, sine of theta 1, sine radians theta 1. Doesn't like that. Oh, radians plural. And then I'm going to cheat. I'm just going to copy and paste. It's the same things. I hope you guys get the idea. So this would be the cosine of theta 2, and it is. This should be L2 times sine of theta 2, which it is. Then we can multiply these across. So I say equals to that guy times that guy. Drag them down. And then I can do the sum, figure out what the total variation of that linkage would be for that set of constraints. The nice thing about this is I can take this like kind of one step further, and I can figure out what is the sensitivity of each of my parameters to my total variation. And you may find out that for something like this, having a longer length, say I make this 20, right? That base length changes the variation that I'm going to get out of the total length. It makes it longer, right? Or I could say that, okay, well, if I change this from 2 to 5, it makes a really big increase in the change in the value there, right? So you can figure out which parameters inside your design are important for either maintaining or destroying whatever the tolerance you need is. The implication there is if you have parts where changing the parameters of the part does not change the overall performance, basically the thing you're trying to preserve, that's a justification for having a large tolerance on that from a manufacturing standpoint, which will save you money. So it's about isolating where you think the most important aspects of the design are, so that way you can not spend a whole bunch of cash. Does that make sense? Any questions on that? Again, pretty straightforward. Excel is going to do this, or not Excel. SolidWorks will do this for us if we specify all of the parameters of the model that we're interested in. But it's still only going to look at this from the standpoint of, hey, I want to maintain this dimension. Here's all the variances that I have. Tell me what the output is. So if you understand kind of this stuff on a more qualitative basis, you can start thinking about how changing an angle or changing a length or specifying a parameter is going to affect the overall kind of performance of your design much more qualitatively, which tends to be faster than doing this all kind of brute force. That make sense? All right, save these files. You guys didn't already do this in your Excel worksheet. Then you can go back and take a look at the video later. For this, I'm just going to save this to my desktop. Got this week 5 folder, and we'll say example by hand. This is not really a by hand example if we're using Excel, but it's more or less a brute force just solving it manually. Right? We're using Excel as a calculator here, right? We're not really using any programming functionality there. The next thing I want to show you is that these are not necessarily accurate. This is a tolerance stack up from a tolerance standpoint, because we're treating all of our kind of output as a linear combination of our inputs. And if we're looking at the actual variance of a part, it's usually not going to be a square distribution. It's going to be some kind of normal distribution. And so if we want to get a better understanding of how that works mathematically, it's good to simulate that in something like MATLAB. So get on Apps Anywhere if you're not already on there. Launch MATLAB. And we're going to get complained at saying that MATLAB's no longer authorized, and we'll just try again. I'm going to try to go to cloud paging and see if I can just launch it from there. Nope, it's not there. Maybe we won't do it in MATLAB. Wouldn't you guys like that? Now that works on the video. I guess I have you guys watch the video again. But I do it live so we can answer any questions if we have them. Requesting authorization. My authorization request being denied. There's too many people using MATLAB. Trying to solve the biomechanics exam. I don't think that's actually it. I do have Edge running. Probably a problem. I'm going to save and close my Excel just to clear out some stuff while I'm doing that. I'm going to go ahead and launch SolidWorks since I'm waiting for it to. No, I think that canceled my MATLAB request. Something went wrong. Need help, please contact support. Virtualizing, authorizing, running. I don't know why, but running SolidWorks and then running MATLAB seems to have fixed the problem. But now I'm waiting for both SolidWorks and MATLAB to run. What we're going to be doing with MATLAB is really running a Monte Carlo simulation. So Monte Carlo, the Monte Carlo Casino is a famous casino. So if you watch like a lot of the Bond movies and stuff like that, it shows up. And a Monte Carlo simulation is really just any simulation where you are trying to predict things that have a known probability of happening. So they're random or somewhat random by running a brute force simulation of all possible things that could happen. So if I wanted to simulate a game of cards, I could come up with all possible combinations of hands of cards that could be produced and then randomly pick them. And then I could play 100,000 games of cards with a certain set of rules that I'm following. And I could see how often do I win. And you could do that as many different times as you want with as many different flavors as you want. and you could try to figure out, is there a way that I can gamble such that I will, always make money? Combination, there's lots of different theories out there of things you could do to win in gambling and always making money. I don't know if you guys have any examples. Have you ever thought about that or done something like that? So one thing that I was looking at, not recently, but a long time ago, is the idea of, say I play a game that has near 50-50 odds. So betting on red or black in blackjack, or not in blackjack, in roulette, right? I double my money when I win, right? And I lose my money when I lose. So if after every time I lose, I triple my bet, I will make back all the money that I lost on the previous rounds. And only when there are enough losses in a row that I go bankrupt do I ever lose. So I have to get, maybe 7, 8, 9, 10 losses in a row to go from whatever's, say I start at $10,000 and start with a $1 bet, right? So I'm able to actually go bankrupt. And what are the chances of that happening? Right? Well, you can run a Monte Carlo simulation to figure out exactly what the chances of that happening are. And guess what? It turns out that if you do that, yes, eventually you run into a streak that is long enough that you lose all of your money, and you do it. And you actually get a curve that looks like two lines that kind of go back and forth. So you have a U1 line and a casino wins line. And the casino wins line goes down faster than the I win line goes up, because the odds aren't actually 50-50. The odds are, 48 or whatever, because is it 36 numbers on a roulette wheel and then the double zero. And if you get double zero, red and black both lose, right? So you have a 1 in 36 odds of losing. And so the difference in that rate is the difference on the odds. So you're really just bouncing back and forth between the casino winning and the U winning, and the casino winning line is faster going down than the U winning line. So if you play long enough, you always are either at this line or that line, right? Or transitioning between the two. But unless you have an infinite amount of money, or you can bankrupt the casino, you will eventually lose. And I can't bankrupt the casino, so. And there's also bet limits. So for people who do have enough money to theoretically bankrupt the casino, right? Like they won't let them bet more than $100 million on a single bet. Right? Have you guys all seen the Iron Man movie? Like he goes in and he's betting and he's like, "What is this, Vegas?" And they have to like turn to the security guard and they're like, "Yeah, let him make the bet." And he does, and he lost, right? Tony Stark. Weird anecdotes aside, so SolidWorks is running, or MATLAB is running. Your MATLAB. But if we want to do a Monte Carlo simulation or something like this, it's a little more useful. We can generate a part. So we have a certain size, some say S1. We'll say it's 1. We'll say this is in inches. And we have a variance, so say var, we'll say V1 equal to 0.1. Again, we can make that in inches as well. And say that the variance of that part is a representation value of like the standard deviation. So it's going to vary around that amount by a certain amount. And if we look at a random distribution, I don't need to use the equals. So the rand function gives us a value between 0 and 1, which is a square distribution. So we could use that. We could also use rand n, which gives us a normal distribution with a standard deviation of 1. So again, it depends on what you're really trying to model. But I'll say we have part 1. We'll say that P1 is equal to S1 plus V1 times whatever we want to use for our distribution. So in this case, I'll use rand n.
Dr. Laura,
Yes,
where did you open that window from?
I opened the window from the new script button in MATLAB.
Okay,
So you click on new script, it'll pop and open an editor. It might be docked. So if yours is like inside one of these other windows, don't worry about it. It's still the same thing,
okay.
right? And so if I do this and I run this once, I gotta save it, I guess. Let me go to my desktop. I'll save it to Monte Carlo. This one, this P1 that I have here represents a specific part, right, that I just simulated. So I can come up with this, I can make another part. Say that we have P2. And I'll just change this to S2, V2. And if I wanted to, I could nest this into another loop here, right? So now I've got two random parts. They have the same parameters, but I have two random parts. And again, if I run this, I get a P1 and a P2. And there's some difference between them. P1 is 1.08 inches big, and P2 is 1.03 inches big, right? But I can generate this, 100,000 times or whatever I want. So let's say for I is equal to, I is equal to 1 to 10,000, 10,000. We'll say P1I is equal to that, and P2I is equal to that. So we're going to save every part that was generated. I'm going to make a for loop. And my favorite command in here is the auto indent or smart indent. If you're ever doing a lot of programming in MATLAB. So we manually said we want to have one part that has a size and the dimension of interest of 1 inch with a variance of 0.1 inches and a distribution that's normally distributed using that variance. We have part 2, which is largely the same thing, right? It's another part with a length of 1 inch, a variance of 1 inch. And then we can say if we stack them together, we can say that total equals to P1 plus P2. And then we can run analysis on those things. So if I run that, you notice that it only took it about a second to generate all those different values. And I can look at the variance, STD. STD dev. I can't remember the name that we use for standard deviation. Standard deviation. STD is for standard deviation. Okay. So we can look at the standard deviation of P1. Yeah, sure, that's what I meant. So it's got a standard deviation of 0.09 for P2, also 0.09. Again, we programmed it to have a standard deviation of 1, but even with 10,000 samples, the standard deviation is not exactly 1, it's close to 1, right? And then if we look at the standard deviation of total, the actual standard deviation of 1.4, right? So the standard deviation of our combined parts was not the linear combination of the standard deviation of our individual parts because they have an equal probability of those variants canceling each other out as they do adding together. And therefore we have a non-linear combination of those values, right? Which is the whole point of me doing this example for you guys, is showing you that, hey, if I take two things with a known distribution and then add them together, you don't always get an output, which is just the mathematical sum of those known distributions, because randomness is weird, right? So you may get things that are bimodal or weird, things like that. And knowing that can be helpful for your design. The nice thing about this, you can also do things like histograms. So I can do a histogram of my total. Show me what the actual distribution of part sizes look like. And I could make that more or less sensitive if I wanted to have more or less bins. And it's useful, right? It's good information for me to have. And I could overlay that with other different things. And I can change parameters, and all those things can come out in any way that I want them to. Does that make sense, everybody? So again, save this. I'll be collecting this, the Excel sheet. If you guys want to elaborate on this, if it's something you want to use for your design projects, then I highly encourage you to do so. You don't need to use all of the tools that we're talking about for your design projects, but I do expect you to see use some of them. If you wanted to go nuts with this, you could say, I could nest for loops to make n number of parts with n number of standard deviations and then run them all over the place. And you could get that kind of stuff too. And you can also make it, back history where there's a previous value, if it won or lost or whatever, you can expand on that. Any questions there? All right, let's take a look at doing this in SOLIDWORKS. In SOLIDWORKS, we can keep it simple as well. So I'm in a new part. I'm just gonna make a 1 by 1 by 1 cube. Actually, let's do it in millimeters. I don't need to change so if I do it in millimeters, my standard precision is 2 decimals. And 2 decimals of precision in millimeters is pretty tight. 2 decimals in inches is not very tight, right? So there's a big difference between 0.1 millimeters and 0.1 inches in terms of what that means. So let's stay in millimeters. We'll do features, extruded boss base, and I'll make it a 10 by 10 by 10 cube. So I'm going to make it 10 inches tall, 10 millimeters tall, sorry, 10 millimeters wide. And I will extrude it to a distance of 10 millimeters. I like using the midplane extrude. Doesn't matter for this case, but I'll put the midplane right in the middle of my part. Again, I don't really care about this part. I'm just going to save it as cube. I will put it in a folder that I want to keep track of because I don't want to make my desktop cluttered again. And then to be able to do a tolerance analysis inside SOLIDWORKS, you have to have the DimExpert annotations on the part first. So I'm going to go into my add-ins. I'm going to turn on Tall Analyst. And then I'm going to go to the MDB Dimensions tab. And then from there, I'm just going to let SOLIDWORKS automatically dimension my part for me. So I'm going to use auto dimensioning scheme. I'm going to use prismatic geometry. And I'm just going to use plus minus just because it's a little bit easier for us to understand. You can use geometric for this and use any tolerance when you want, but you have to have one of the two. I'll just do 3 orthogonal faces for my datums. And that's going to set up my coordinate system for the part. And I can leave all features selected because, again, this is a very simple part. So it's just going to have linear dimensions anyways. You see I got 3 dimensions here. So 10 millimeters plus or minus half of a millimeter, 10 millimeters plus or minus half a millimeter, 10 millimeters plus or minus half a millimeter. It's assuming that all of these faces are orthogonal to each other and they're all parallel. It doesn't really say that to me explicitly, but with linear dimensioning, you don't have that much detail. If we're going to geometric dimensioning, we could specify how straight each of the sides were to each other, basically what the parallelism are. And again, that's one of the reasons that we like geometric dimensioning and tolerancing better than linear dimensions, is that it's much more explicit about what the requirements are. But for the stack analysis, we're fine with just doing this so you guys can see how this tool works. So save that cube. Anyone have any questions on getting those dimensions on there? We do need to have these on these before we can do a stack analysis. I'll mention it now because I might forget to mention it later. What it's going to use for the stack analysis is not the actual geometry of the part. It's going to be these planes that are specified with the annotations, right, inside our stack. So if I don't have those annotations for the location of those faces in the tall analyst or inside the MDB dimensions, the tall analyst won't be able to do anything. I'm good? I'm going to make assembly from part. I'm going to save this first just to make sure it's saved. make assembly from part. Wait for it to load. Click on the green check mark to bring in the cube. I'll right click on this guy. I'm just going to copy him. Actually, I'm just going to do Control C, Control C, Control V, Control V. So I'm going to get 3 cubes, 1, 2, 3, and I'll mate them all. This is probably a good chance for me to use like the quick mate, although I don't think I want to. So I'm just going to use coincident mates, and then click, click, accept, click, click, accept, click, click. I'm just going to make a little chain here of my cubes. The actual domains, the actual mates that you use here don't matter. As long as you have a stack of cubes that are fully defined, you're set. So if they're stacking up or down or left or right, doesn't matter. Anybody having any issues getting the cube stack set up? Try and post these files after class too, in case you guys want to take a look at them. But they're pretty straightforward. So imagining most of you don't have too much time to putting them out. Hey, Drew, I'm not sure what you did. Are you in an assembly?
Yeah.
Oh. You have like a configuration manager or something pulled up. I don't know.
Yeah, anytime I Control C.
Let me see. Maybe you're hitting Shift C or something. Maybe, yeah. I don't know, wrong hotkey. Once I've got these 3 cubes laid out next to each other, now I can actually use the tall analyst to do the evaluation that I want. If you to search for tall analyst study, it'll come up. You also go into tools, MDV dimension, tall analyst study. You can also go to the dim expert icon here. It's not the configuration manager. I don't know why it's like offset by 1. And then it's on the very right. If you don't see that, you may have to make this a little bit bigger, depending on how wide your screen is. I don't know why they don't give you a little scroll button there or something. So 3 ways to get to it. Search for tall analyst study, go to tools, MDV dimension, tall analyst study, or go to the dim expert manager tab in your command properties, and then click on tall analyst study. And then we say, what do you want to measure? I'm just going to measure the total width of this stack of cubes. So starting on one end, all the way to the other end, saying, hey, is that the dimension you want? I say, yep. Once this turns green, it's got everything it needs to move to the next step. Similar to, what were we doing that was using this type of tool? I forget which other tool we were using, but similar to some of the others and tools in ThoughtWorks, this one you have to go through each of the pages step by step. We were doing, copy mates. I think also some of the tools inside of the CAM that we're using have the similar function. So this is green. We don't click on the green check mark. We go to the little right arrow, and it goes just to the next page inside this part. It says, okay, well, to get from there to there, we need a component sequence. So we're going to start with the one on the right. And then we're going to go over to the one on the next one and the next one. You see now it's got enough. It turned green and I can go through there. I don't know if I go back and forward, but undo that. I think I've just like clicked on them to do it. So I was going to start with on one side. And it adds that to it. It says, hey, you don't have enough parts yet. Okay, we'll keep adding parts. Now we've got enough parts. We do this. One of the reasons it does this is that if you have a complicated assembly, you probably have parts in that assembly that are not contributing to the stack up that you're currently doing the analysis on. So this makes it easier for SolidWorks to not, run 1,000 different parts that aren't going to change the overall dimension of whatever it is you're trying to measure in the assembly. So in this example, that step seems redundant. In most practical applications, it's very important because you're trying to narrow down the study. Then after we've got the part sequence specified, hopefully it'll let us specify what the relations are between the different features. There we go. So cube 1 is already defined. It knows where it is. We're on cube 3, which is my middle one, because I didn't pay attention to the order I did them in. It says, hey, how are these things aligned? It says that these different planes are aligned, 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 aligned. It's basically all the possible ways that those cubes could be aligned relative to each other. And you'll notice there's 5 alignments that it specifies, even though I only added 3 mates. So it really doesn't matter what mates you're using. It's just looking at the faces themselves. So I'm going to click on the kind of the joining face as the primary. I'll make the bottom ones the secondary, and then I'll make the side one the tritary. That's basically saying how are these things aligned relative to each other. And it's going to use that to do the transformation from one part to the next part. So first part moves by a certain amount based off of all the different planes that are defined in the tall analyst tool. When those planes move, how do the planes on the next part move? That moves the origin of the next part, and then it applies that part's dimensions, and then it moves on to the next one. So it's sequential, kind of like we do in our tables over here, going from top to bottom. That's got a green check, we'll move to the next one. And the same thing, I'm just going to do the kind of touching faces as the first alignment. The bottom faces as the second alignment, because it doesn't really need the rest of them on this one. I want to put them there anyways, because it already turned green on me. And then the side faces at the third alignment. And we're green, we can go on to the next one. I think on this one, it probably only needs the primary because things are so simple. Then it says, hey, here is our results from the simulation, right? We have a nominal size of 30 millimeters. We have a minimum of 28.5 and a maximum of 31.5. The root sum of squares minimum is 29.1. The root sum of squares maximum is 30.8. And so what this is doing is it's really giving us a breakdown of what the bounds are, as well as what the expected values would be if we assumed a normal distribution of those part size variances. So it's kind of running like the by hand calculation that we did and the Monte Carlo simulation and saying, hey, this is what you can expect to get. And you can see that the RSS values are kind of in the middle of those maximum values, because there is some kind of potential for those tolerances to interfere in a way that is beneficial to us in terms of maintaining the nominal size of the dimension, right? And we can display this. So it's actually showing us the maximum value as the sharded leg. We can change that there. So there's the max and the min. And it also shows us the contribution of each of the different constraints to the overall size. So if you wanted to know which of the variances of the parts was the most significant on the output, it would give you that. In this case, since they're all the same, the variance contributes equally, and so they're all 33.3%. And if you want, you can export these results, and it just gives them to you in Excel. I think I saved that to a bad spot. I'm just going to go to, just because I want to make sure I have it in the folder that I actually want. I'm going to export it again. But you can see here, there's not a whole lot of detail in here. It just tells me the nominal value. Tells me the type of dimension that's being used to drive each of those things. So there's a distance between, there's the tolerance on it and the tolerance type, the contribution of each of those, the maximum, the minimums, right? And then the different planes I used. The nice thing about this, if you wanted to reconstruct the analysis in SOLIDWORKS with the part files, assuming you have part files, you could rebuild it from this. So if you lost it for whatever reason, or if you wanted to give it a report or somebody, you don't have to copy and paste from the prompts, so you can just pull it from the Excel file directly. Click on the green check mark. It's still there, just hidden. So if you want to go and look at the results again, you just double click. Maybe you have to do edit feature. Yeah, and then it comes back out. So, and it should save with your part, or with, in this case, with your assembly. So if you save the assembly, you can close it and come back to it and look at it again. Change the parts, add more parts, subtract parts. If you add or subtract parts, you probably just have to rerun the study. And honestly, you probably have to rerun the study even if you change the parts. Make sure the dimensions update. Any questions or concerns about that? So pretty straightforward. On Wednesday this week, we're going to talk about, okay, well, so if we can analyze our parts to figure out what the variances are, given some standard deviation or whatever we specify as the inputs, what are some things that we can do in our designs to make them more resilient to variations in size? So we'll talk about sizing holes appropriately based off of the constraint you want them to include. We'll talk about compliance, and if you want to have compliant or rigid members. We'll talk about some of the things you can do in SOLIDWORKS to help figure out some of those feature sizes. So even things like derived parts and assemblies and things like that. Then on Friday, we'll have a practice CSWP problem, and we'll do just some group work. Or we'll do tests on your bridge. We do bridge testing on Friday, right? Let's take a look at the schedule since we're already. Next week must be our bridge testing. We can do test testing. I have the schedule for the bridge project posted on the page here. So 16th, I was hoping you guys would have your practice bridges to me. But even if you send them to me tomorrow, and I can print them tomorrow. And then the 21st, which is Friday, right? 21st, we want to do the actual testing of the bridges. And then the 23rd, you guys have to submit your reports. So the deadline on here is for you guys to submit your reports, not to submit your bridge files for printing. I don't need the whole report or really anything more than just the STL for the print. But if you want to send me your simulation results and things like that with your file, I can give you feedback on that as well. So that way you have some idea of what your grade would be hypothetically on the assignment later on. Does that make sense? And if your bridge doesn't actually hold 50 pounds, it's not like you're going to fail the class. It's just you won't be the winner unless you can hold 50 pounds. And then we start looking at how light and efficient is it, right? So you got to meet the primary design criteria first, and then secondary design criteria is the print time. That's a really good question, and I don't remember what the print times for the bridges were last year. Probably a couple hours at least. Yeah.
Because in there you say like a couple of minutes, and I'm like, I could not get the bridge that could hold 50 pounds.
Where do I say? I'm saying here. I may have said it in one of the videos. I don't see anything in here about how long your print should be. I think I was able to get the one that I test built last year down to like 16 minutes, but remember that didn't work, right? It failed. Now that you couldn't get one down to that much time and have it work, it's just the one that I did not. And honestly, I haven't redesigned my one for this year yet. So I'm probably in the same boat as y'all in terms of procrastinating on that. All right, well, let me know if you have questions. We will stop the recording and